Hello, my name is Mohammed Noor, and I'm a professor at Duke University. I'm very excited to be talking with you about genetics and evolution. Here in this first video, we'll be looking at what is evolution, and in some of the subsequent videos, we'll look at the evidence for evolution, and we'll look at responses to criticisms of evolutionary theory. So let's dive right in. Evolution, in a biological sense, is simply change through time. And very importantly, that is change through time over generations. So for example, the human species hundreds or thousands of years ago was much shorter than it is today. Over the course of those generations, the human species has grown taller. That change is an evolutionary change. In contrast, I used to be a baby, now I'm an adult. That change is not an evolutionary change because it happened within an individual. That change is development instead. Now, one common source of confusion is the distinction between evolution and natural selection. Evolution, as I mentioned, is simply change through time. Natural selection is one driving force of evolution. It can be one reason that evolutionary change happens. But importantly, it is not the only reason evolutionary change happens. Later in the course, we'll talk about other forces that drive evolutionary change. But let's start by looking at one famous case of evolution by natural selection. A classic example of evolution by natural selection is that of the peppered moth, Biston betullaria. I have here a picture of two of these. There's one peppered-looking one that's mostly white with little black flecks, and one black form over here. It's often referred to as melanic. Which of those is harder to see on that tree? Probably for most of you, the peppered form is a little bit harder to see because it blends in with the color of the tree and the spotting pattern of the lichens that are growing on the tree. In contrast, this black one is very easy to spot. Not only is it easy to spot for you, but it's also easy to spot for hungry birds looking for a tasty moth treat. As a result of this, the black forms tended to get eaten much more than the white forms, and in 1848, nearly all the moths that lived tended to be peppered. Now things changed with the Industrial Revolution, that trees were blackened and a lot of the lichens died. So instead of having this form be the camouflaged form, all of a sudden the black form had an advantage on these new black trees. Because of this change, 98% of the surviving moths were now black, and the peppered forms were largely gone. This was not a change in the color of individual moths. What happened is the offspring of the black moths were able to survive because they could hide. They were better camouflaged. Meanwhile, the offspring of the peppered moths were not so lucky, and they got eaten up by a lot of the birds. So this change from being nearly all peppered to nearly all black in this species is referred to as industrial melanism. That is change in the coloration of a species to a darker form in response to pollution in the environment caused by humans. This happened not just in the peppered moth, but in a wide array of insects and other species. This process continued until about 1952. In 1952, in Great Britain, we had what was referred to as the Great Smog. The Great Smog brought in a ton of smog, as you would guess, that sat over the city of London for weeks on end. Tons of people died from this. This was a terrible amount of pollution. This picture is taken in broad daylight. It was incredibly hard to see. Ambulances didn't run. And in fact, it was even seeping into homes and performance venues. A lot of theaters closed because even inside the theater, so much smog had come in you could no longer see the stage. As is typical with a lot of politicians, it took a disaster before they could actually act. And what we had in Great Britain was the passage of the Clean Air Acts in 1956 and 1968. The passage of these acts cleaned up a lot of the environment. What you saw happening then was those trees that had previously been blackened were able to get cleaned off, and a lot of the lichens on them started to grow back. In response to this change in the environment, we also had a change in the peppered moth. So this was a case of evolution from white to black, and now from black back to white. This picture shows the change in the fraction of moths that were black over time. So starting in 1959, again, most of them were black, as we just said. So we go into the 1980s, we see a drop in the fraction of these black moths. 1990s, further drop. And in the 2000s, it's actually hard now to find a black form of this peppered moth in Great Britain, in the United States, in Japan. The same process happened on multiple continents. So this is a case of evolution by natural selection. So one question a lot of people have asked me is, isn't evolution by natural selection just a theory? Well, I will argue to you that evolution by natural selection is a mathematical inevitability. There is no way to avoid having evolution by natural selection if some very simple conditions are met. So let's imagine you're working with a population of squirrels. I used to live in Louisiana. Every April, we'd have an explosion of baby squirrels all over the place. There'd be baby squirrels running around in the yards, on the sidewalks, and kind of unfortunately for some of them, out into the streets, where they'd often get hit by cars, sometimes by me. This was very unfortunate for the squirrels, as you can imagine. Now let's imagine that you're looking at a population of squirrels of two types. Let's say there's a type A that runs randomly, and is likely to run out into the street, or possibly, not running into the street. And let's imagine there's also a type B that fears asphalt, so they avoid going into the street. There would be an advantage to the type B offspring because they're much less likely to get hit by a car if they don't go out into the street. So let's say that on average, the type A squirrels have one offspring and then they pass away, whereas the type B squirrels have on average two offspring before they pass away. So we'll start a population with half type A, half type B, and let's see what happens. And we're assuming that type A individuals have type A kids, type B individuals have type B kids. After one generation, these type A individuals each have one offspring, so we have now a new population of 100 type A squirrels. The B ones, as I said, are each having two offspring, so these 100 produce 200 kids. So what's happened? Instead of having 50% B, all of a sudden now we're 66% B. It's 200 out of 300. So let's go another generation. Well, these 100 have another 100 for babies. These 200 would have how many? They'd have 400 because, again, each of those 200 has two babies. We're assuming, again, the parents pass away. So we've gone from 66% to 80%. 400 out of the total of 500. Finally, generation 3, 100. And over here, we have 800 squirrels. So we've gone from 80% now to 89%. That is evolution by natural selection. We see this change over time, over generations, very importantly, from 50% type B to 89% type B over the course of 3 generations, 3 new generations. So let me ask you this question. Why is evolution by natural selection contentious to the general public? I'd like you to think about these 2 questions for a minute, and then Coursera here will ask you a question. Are there any holes in the theory of evolution or in the evidence for evolution that you know of? And does it apply to humans? Think about that for just a moment and then answer this question. And I hope you enjoy the next video.